Okay, so we are getting ready for the exam tomorrow and going over material to review on taking derivatives and techniques of derivatives. And so I thought I would just kind of throw some problems and we would go through them. So let's see. What if you were asked to find the following derivative? So these questions, when you're taking the exam, are kind of scrambled in the order, and so it might not be like the same order that we have looked at things. I'm pulling questions that are kind of similar to what you might be seeing on the test. Let's assume the following. Let's say that you were given that the derivative of your function of x at 3 is equal to -8. You're given if you took the derivative of g of x and evaluated it at 3, you get 1/5. And y is equal to f of g of x. And so it wants to know, what is y prime at x equals 3? So I noticed that y is a composition of two functions. And so when I take the derivative of y, we need to use the chain rule. And so that is the derivative of the outer function of our inner function, g of x, all times the derivative of our inner function, g of x. And so if I wanted to figure this out when x is 3, so I'm going to go in there and I'm going to plug in 3 wherever I see an x. So this is f prime of g of 3 times g prime of 3. I missed one piece of information, that g of 3, so this was in the definition or in the problem itself, g of 3 is equal to 3. Okay, so that piece that I missed, notice, is our inner piece of our function of the derivative of f of x. And so if we replace what g of 3 is, which is 3, this would equal the derivative evaluated at 3 times the derivative of g of x evaluated at 3. So it already gave us what the derivative is of f of x at 3, which is -8. And it gave us that the derivative of g of x at +3 is 1/5. And so we can simplify by just multiplying straight across. Nothing simplifies in the numerator and denominator, so we get back -8/5. Okay, so given information about derivatives of the function at particular values, the original function at particular values, you should be able to answer different types of questions. So let's suppose you're given the following. Your x value what your function is at that x value for f of x, what your function is for that x value for g of x, what f prime of x is, and what g prime of x is. And so when x is equal to 2, we get back 6, 2, 1/5, and -5 in that order, respectively. And so if x is 3, so going horizontally, you would get 2, -1, pi, or 5. And so asking the following questions. What is suppose the function f and g and their derivative with respect to x have the values shown at the right, x equals 2 and x equals 3. Find the derivatives with respect to x of the combination below at the given value. Okay, so on all of these, we're going to be trying to find the derivative at that value of x. Let's see if I can get this down there. So first one we want to look at is, what if it was f of x over g of x? And we wanted to find the value of this when x is equal to 2. Okay. So I'm just going to say this is y equals f of x over g of x, just so I can write the notation. And so when I take the derivative of y, I notice I'm going to have to use the quotient rule. And so dy dx, or y prime of x, another way to write it, this is equal to, well, quotient rule says take the derivative of the numerator, so f prime of x, all times the denominator, g of x, minus the numerator, f of x, all times the derivative of the denominator, g prime of x, all over the denominator, g of x squared. And so we wanted to look at this when x was equal to 2. And so we want to go back in, and wherever we see an x in this equation, we're going to plug in 2. So we have f prime of 2 times g of 2 minus f of 2 times g prime of 2 all over g of 2 quantity squared. So I need to go back and look at my table, and all you're doing in this case is going in and plugging in what those values are. So f prime of 2, so I'm looking at when x is 2, what is f prime of 2? And so I notice that that is 1/5. I'm going to be multiplying that times g of 2, so 1/5 times 2. Just write that real quick. Minus f of 2 times g of prime of 2. While I'm at it, because I know that g of 2 is 2, let's just put that in the denominator, and we're going to have to square that. And we can think of that 2 if you want, if it helps, as 2 over 1. Okay, so minus f of 2 g prime of 2. F of 2 was 6, and g prime of 2 is -5. So 6 times -5. Okay, so let's simplify. 1/5 times 2, that's 2/5. Minus, well, minus -6 times -5, that's actually a plus. So plus 30, all over 4. So in order to deal with this mix or this complex fraction, I need a common denominator so I can combine the numerator as one fraction. Or the other thing is I can multiply by 1. A fancy one to clear that fraction, I can multiply every term by 5. 5 over 5. Maybe faster. I don't know. So if we distributed that 5 to the 2/5, the whole point of multiplying by the 5 was so those 5s would cancel. The denominator would go away there and we be left with 2 plus 5 times 150. I'm sorry, 5 times 30 is 150 all over 5 times 4, which is 20. So we get 152 over 20. I noticed that at least 2 goes into those because they're both even. We might have something else that goes in there too. Oops. So this would give me 2 goes into 20 10 times, 2 goes into 15 7 times with a remainder of 1, 2 goes into 12, so that's 6. So that's 76 over 10, that means 2 goes into those again. 2 goes into 10 5 times, 2 goes into 7 up here 3 times. Remainder, so 2 goes into 16 8 times. Okay, so our derivative of f of x over g of x evaluated at x equals 2 is going to give me the 38 over 5. Okay, so sorry, it keeps on jumping back. But looking at this problem, so you should be able to do certain questions like that. So this kind of shows me that you understand what the formula is, the quotient rule, or if it had the product rule or the chain rule, without having to go through long, extraneous steps to save some time, although you will have some of those problems too. So let me see if I can get to a new page. Start a new page up here. Darn it. Why do I always have so much problems? Okay, there we go. So you should be able to take derivatives with e. Are you guys okay with that? You should be able to take derivatives with natural logs. You should be able to use logs to help you take derivatives. You should be able to take derivatives of your trig functions and your inverse trig functions. So any of those in particular you guys want to see first?
We do a log function one.
Yeah, so what if you have what if it was y equals the natural log of the natural log? Let's say of 2x. And we want to find dy dx. Okay, so I need to look at what type of things that I'm doing here when I take the derivative. And so I have a natural log of a natural log function. So to me, that's telling me that I'm using my chain rule. And so there's a couple different ways that we can do that. Looking at dy dx, if we look at the outer function, remember when you're taking the derivative of a natural log, it is just 1 over what you were taking the natural log of. So that would be 1 over, in our case, what we're taking the natural log of is another natural log, 2 of x, times, then it was the derivative of the inside. So what you just put in that denominator. And so the derivative, let me just write that, we're going to take d dx of ln of 2x. Okay, so let's just do that then. So we have 1 over the natural log of 2x. But if I'm taking the derivative of ln of 2x, so same rule. So I'm taking derivative of natural log is 1 over the natural log of what you're taking. I'm sorry, is of what you're taking, not the natural log. So this would be just 2x here, times the derivative of the inside. And so the derivative of the inside of the natural log in this case is the derivative of 2x, which is just 2. So multiplication of fractions, we can just multiply straight across. But I notice I have both a 2 in my numerator and a 2 in my denominator. And so we can actually simplify that by crossing that out. And so we're left with 1 all over x. I'm just going to put that in front of my natural log of 2x. I don't have my chat on, so if you guys are asking questions. Inverse trig after, okay. Okay, so inverse trig functions, I don't have those memorized, but I know I can quickly memorize, or not memorize, I can do these by using the right triangle. And you guys are going to be doing that a lot when you get into Calc 2. It's been a while since I taught it, but I remember you use that over and over and over again, and you use actually tangent inverse a lot. But let's look at this problem where we want to find the derivative of y is equal to cotangent inverse of, I don't know, let's say 1 over 6x squared. Okay, so personally, I do not know the derivative of cotangent inverse. I'd actually have to, unfortunately, derive the derivative of cotangent, but I know I can do that pretty fast. And so I would quickly, actually, I'm going to take the cotangent of both sides so I can get rid of that inverse function. So if because we can do this because it's an equation, if we take the cotangent of both sides of our equation, a function and its inverse, or composition of a function and its inverse, always gives you back what you were doing. So in this case, it would give me back 1 over 6x squared. So let me write that. So I have cotangent of y is equal to 1 over 6x squared. Okay, so let's think about this and let's create a right triangle using this information. And so I have some angle y, and I need to remember the relationships of sides for cotangent. Okay, so cotangent, and I have to go through this in my head, is cosine over sine. I know that cosine is adjacent over hypotenuse, sine is opposite over hypotenuse. If I invert multiply, I would get that this was adjacent over opposite. I should have just did the reciprocal of tangent. That would have been faster. But anyways, sometimes you don't think of the easiest way when you're going through problems. So cotangent, you have your angle y. We know adjacent to that angle y, which is the side sandwiching it, that's not the hypotenuse. So this is down here is 1. And our opposite side is 6x squared. So I need to figure out what this length of my hypotenuse is. And so we have a right triangle using the Pythagorean theorem. I know it's the square root of the sum of the squares of the legs. So summing 1 squared plus summing that quantity 6x squared. So this gives me the square root of 1 plus 6x squared times 6x squared is 36x to the 4th. Okay, there's a sum in between those two terms. If that was just one term, I could break it down because those are perfect squares, each of one of them. But because of the sum there, that's not the same as the square root of 1 plus the square root of 36x to the 4th. So we got to keep it like that. Okay, so that was just to do my triangle. So that's kind of like side work so that when I take the derivative, I can use this to help me. And so right now, what we want to do is we want to take the derivative of this piece right here. And so we're going to use implicit differentiation. And so taking the derivative of both sides of our equation, well, the derivative of cotangent y. Equals the derivative of the other side, 1/6. I'm going to rewrite that x squared in the numerator, or denominator. I'm going to move it up to the numerator. So we could rewrite that one side as 1/6 times x to the -2 power. That way I don't have to use the quotient rule when I'm taking the derivative of the right-hand side. Okay, so this is where I said, unfortunately, I did not memorize these, but I know that fortunately I could probably get it pretty fast. So I have to kind of remind myself how to take the derivative of cotangent, because I know how to take the derivative of cosine and I know how to take the derivative of sine. So I could basically figure the derivative of all the other trig functions by knowing that. And so y is equal to, again, cotangent. I'm going to say y equals cotangent of x. So cotangent of x, that was again cosine of x over sine x. I'm just going to do this really quick. Taking the derivative of this, I have to use the quotient rule. Derivative of cosine, that was negative sine x. Derivative, or times the bottom, sine x. Minus the top, cosine x, times the derivative of sine x, which is cosine x. All over the bottom, sine x, quantity squared. So this is negative sine squared x minus cosine squared x all over sine squared x. I notice that this is almost identical to my Pythagorean identity. Cosine squared plus sine squared is 1. If I pulled out a -1, that would be the same, that would be the same thing as -1 times cosine squared plus sine squared, which is the same thing as 1. So this is really 1 over sine squared x. Oops, negative. 1 over sine, that is cosecant. And so this is negative cosecant squared x. Okay, sorry, but that I had to do to take the derivative of cotangent y. So taking the derivative of cotangent y, we know that this should be negative cosecant squared. My angle's y though, not x. I was just doing that on the side. Do not forget, we're using implicit differentiation, and y is in terms of x. So we have to multiply by dy dx is equal to, so I'm going to just keep my 1/6 here and take the derivative of x to the -2. Bring my power down front, -2, subtract 1 from my power, so x to the -3. Okay, so almost there. I can get dy dx. I'm going to divide both sides by negative cosecant squared y, so I can get that dy dx by itself. At the same time, I'm going to kind of clean up the other side. So notice the 2 and the 6. We can reduce that, and we can also bring down that x to the -3 into the denominator. So this will be equal to, so -1 all over 3. X cubed is coming down to the denominator. And we just divided by this negative cosecant squared y. Okay, so I noticed too that I had 2 negatives. That's going to end up becoming positive. And I'm almost done. I need to figure out what cosine squared y is. So if we go back up to our triangle, we can figure out what that is. So 1 over, let's just do this, 3x cubed cosine secant squared y. Well, let's first figure out what cosecant y is. So cosecant is 1 over sine. So that's going to have to be hypotenuse over opposite. So we're looking at our hypotenuse side. If I remember right, was the square root of 1 plus 36x to the 4th. All over the opposite side, which I think was the 6x squared. Yep. So if we go in here and we replace what cosecant squared y is, well, that was just cosecant y. So let's actually square both sides so that we could figure out what cosecant squared y is. It doesn't want me to change colors. Okay, so squaring both sides, let me just do it here. I have cosecant squared y is equal to, well, if I square the numerator, that's just going to cancel out my square root. So it gives me 1 plus 36x to the 4th. And if I square the denominator, that's going to give me 36x to the 4th. Unfortunately, I cannot cancel those because of this addition in the numerator. And so rewriting this, I get 1 all over 3x cubed, all times cosecant squared y, which we just found was 1 plus 36 x to the 4th all over 36 x to the 4th. So we want to clean it up. We don't like fractions within fractions. I noticed that we have some things that will also cancel. This is a single term here, 3x cubed, and it's multiplication in between, so I can cancel with a 36x to the 4th. So my word is frozen, so you guys are not going to get any more color today. So it changes. So 3 goes into 36 12 times. I know x cubed cancels with my x to the 4th, leaving me just with a single x. I notice that now I have just a 1 over a single fraction, so I can invert, multiply, flip that up. And so this would equal 12x in the numerator now, all over 1 plus 36x x to the fourth. And there's nothing that simplifies. And we're done. Okay, so questions on that? Is there another type that you guys want to go through?
Oh, I had a question on that problem.
Yeah.
So on the second to last step, we were like crossing out the 36 right there. Where did you get the extra 6 and the extra x?
Because I have an x cubed here divided by x to the fourth. And so if I use my rules of same base exponent, you subtract. And so I'm left with a single x in the denominator of the denominator. That makes sense?
Yeah.
Any other questions on that? So in a way, that's a good problem because it also showed us implicit differentiation, which you guys are going to have 2 on the test. So let's how about let's look at, here we go. I'm going to have to just move this down and then I'll move it back up. Okay. What did I want to do? Okay, so we have y is equal to, how about the square root of x squared? I don't know why my computer's acting up. I'm gonna try something different. I'm gonna try sharing a different screen with you. And maybe in the long run, this will be better, but I don't know. Can you see just a white screen?
Yeah, that's all we see.
Okay. And so now you're seeing me say example. Maybe. Let's say y is equal to the square root of, I don't know, I just really want to make it nasty, 5x to the 5th.
Are you writing?
I am, so you're not seeing
Okay,
that?
yeah, we're not seeing that.
That's too bad. Okay, let's try something. Now, can you see it?
Yeah, now I can see it.
Well, that's not the screen I want. That's the one I have to write. I can't write on that monitor. Stop share that. Okay, can you see my monitor again?
Yeah, we can see it.
Okay, so I'm changing it up now because I right here has the x squared. So I have y equals the square root of x squared. Well, that's not plus 1 inside the parentheses. Let's say all times sine of x all over x plus 3 all times x minus 1. And it says find dy dx. Okay, so I shudder when I see that. I made it so maybe you would shudder when you saw that. Because notice that we're going to have to use the quotient rule. Within the quotient rule, we're going to have to use the product rule in the numerator, product rule in the denominator. We're going to have to do derivative sign, trig functions, and we have a quotient rule, or not a quotient rule, a chain rule. And so this is where taking logs and using properties of logs is really helpful. And so we can take the natural log of both sides of the equation. So we're going to use logs to help us. And so if we took the log of both sides, I want to take the natural log just because I know if my log is not base e, then there's a little bit more to the derivative, where it was easier to take the derivative of a natural log than any other base of a log. So I'm going to take the natural log of the left, which is y, is equal to the natural log of the right, which is the square root of x squared plus 1 sine of x all over x plus 3, x minus 1. So I get the natural log of y is equal to. So now we want to use properties of logs to rewrite this as a sum or difference of multiple logs. And so I noticed that we have division. So I can break down the division with subtraction. So that would be the natural log of my numerator minus the natural log of my denominator. So I have the natural log, and at the same time, I'm going to rewrite the square root of x squared plus 1 to be the power of 1/2 instead. So I have x squared plus 1 raised to the 1/2 power, all times the sine of x, minus the natural log of my denominator, which is x plus 3, all times x minus 1. So we have the natural log of y is equal to, so remember natural log, if you have a natural log of what something's being multiplied, we could rewrite it as a sum of the product. And so this would be the natural log of the first piece, x squared plus 1 to the 1/2. All plus the natural log of sine of x. Okay, so that minus is going to have to be distributed when I break that as a sum. So this is really going to be minus minus. So minus ln of x plus 3 minus the natural log of x minus 1. So now when we take the natural log, and taking the derivative of the natural log, remember it's just 1 over what you're taking the natural log of times the derivative of the inside. Also remember, another property of logs is if you have a natural log of something raised to a power, that power can come down front. So I'm going to move this power down front. And so I'm going to take the derivative of both sides. I don't want to have to write that I'm going to take the derivative of both sides. So taking the derivative of natural log of y, that is 1 over y times the derivative of y, which is dy dx, 1 times dy dx, is equal to, so bringing this down, that was 1/2, but then derivative of natural log of x squared plus 1, so that's 1 over x squared plus 1, times the derivative of the inside, which is just 2x, plus, so 1 over the sine of x times the derivative of sine of x, which is cosine of x minus, so the derivative of natural log of x plus 3 is 1 over x plus 3 times the derivative of x plus 3 is just 1. I'm just going to put it there so you remember that you don't forget it on other ones. And then minus 1 over what we're taking the natural log of, which is x minus 1, times the derivative of x minus 1, which is 1. So we're almost there. We're going to multiply both sides by y, and then we have dy dx by itself. And then we can also clean it up a little bit. I noticed this 2 cancels for the first grouping on the right-hand side. I also noticed cosine over sine. I could rewrite as cotangent if I want. Just for time's sake, I'm not going to multiply by that y and simplify it, if that's okay. So I'm thinking that I might have to limit. I think I might have made your exam way too long. Some of these problems have a lot of steps. But I haven't actually sat down and taken what I've written out so far. So any other ones that you guys want to approach? We didn't look at an E. We did look at inverse trig. We did look at taking the derivative of trig. We didn't do a product rule, but I think you guys could probably do a product rule pretty easily. So we have like 7 more minutes. Anything that you guys really want to see? What about
the tangent line?
What was that?
Sorry, I just said maybe 3.1's find the tangent line.
Okay, so finding the equation of a tangent line.
Yes.
Okay. Okay, so when we're finding the derivative of a tangent line, basically what we want to do is we are given the function and we want to find the derivative and evaluate the derivative at the value that it wants the tangent line. And that's giving us the slope at that particular point of the line. We also need the point of the line, a point on that line, which we could figure out. Just plug in that x value into the original. And then we have a point and a slope. So it shouldn't be too bad, hopefully, to find the equation of the line then. So looking, let me just pull one. So what if it was f of x is equal to the square root of x, and it wanted you to find the equation of the tangent line. At the point 4, 2. So actually we have the point, and you could see that that's the point. If you plug in 4 for x, you get back 2 for y. So that's already given us some of the work. We need to figure out what the derivative is. And so taking the derivative, I would first rewrite f of x as x to the 1/2 power. And then I can use my power rule. So bringing my power down front, I get 1/2 x, subtract 1 from 1/2. I get negative 1/2. So this is really 1 over 2 square root of x. Okay, so that is my derivative. I need to figure out what my slope is when x is 4. So I need to figure out what f prime of 4 is. And so I get 1 over 2 times the square root of 4, which is 1 over 2 times 2, which is 1/4. So I have an equation of the tangent line, the slope of the tangent line is 1/4, and we have a point of the tangent line is at 4, 2. So I tend to like to use my slope intercept form and find out what my intercept is. Some of you used your point slope formula. Either way, we're going to get the same result, maybe look at a little differently. I would plug in my x and my y value into y equals mx and my slope into y equals mx plus b and solve for b. So doing that really quickly, I have 4 is equal to, sorry, that's my, it's not going to let me erase. Maybe it is. That was my x value. My y value is 2. 2 is equal to my slope of 1/4 times x, which is 4 plus b. I see that that reduces. 2 equals 1 plus b. If I subtract 1 on both sides, b is equal to 1. And so I know my equation of the tangent line is y is equal to my slope at that x value, which is 1/4 x plus b, which we just found to be 1. So we found the equation of the tangent line when x was 4 on the curve f of x equals square root of x. Any other ones?
Is
Can we
there
do
any?
one with, oh, go ahead.
Oh, thank you. Is there any way we could look at a word problem that's like a light is moving along a wall, and it creates this angle, that kind of thing?
Okay, so don't worry about that because that is from 3.10, I believe, the related rates. So like the rate the angle was moving. So
Okay.
that won't be on this test. But remind me later and we'll do one when we're studying for the next test.
Okay, thank you.
And then in chapter 4, we're going to see more related rates again. And so that might help too with that section. But don't worry about that for this test. Salvador, did you have a question?
I was gonna say if you can like do one like using like E
Yeah,
real fast.
of course. Okay, so let's say, what if you had y is equal to e? What if it was e to an e to the x squared? Okay, so derivative of e. Remember the derivative of e, it's just the derivative of the exponent times itself.
So
Okay,
we
but
want
I
to take
know,
the natural log of both sides.
you know what, we actually could, and that might be easier than the way I was gonna go approach it.
But-
So
Just because, a natural log tends to have E in it, as its sub,
and you're right. And the natural log, if I took the natural log of e, natural log on both sides, that would clear out my e and leave me with just
Yes.
the exponent. So either way, I wasn't going to go that way, but we can do that way.
Okay.
So I would take the natural log of y equals the natural log of e raised to this exponent, e to the x squared. So I have natural log of y is equal to, again, natural log of e. This is saying e to what power gives you back e to this power, which is its power, e to the x squared. So now I need to use implicit differentiation when I am taking the derivative of both sides. And so implicit differentiation of a natural log of y is 1 over y times the derivative of y, which is 1. But y is in respect to x, so dy dx equals, so again, derivative of e is just the derivative of the exponent. So derivative of x squared is 2x times the original e function itself, e to the x squared. And so to get dy dx by itself, we would multiply both sides by y. And we would get y times 2x e to the x squared. So let's just go back in and replace what y was. Y was our original piece. So that e to the x squared all times 2x e to the x squared. I notice I have the same base of e. I could technically, if I really wanted to, remember if your multiplication, same base, you add your exponents. The thing is, if I add my exponent e to the x squared and x squared, they're not like terms and I couldn't simplify it. So I might as well just leave it like that. Any other ones? Hopefully I'll be able to save that for you guys. Stop sharing this. Let me stop videoing. I hope I videoed. Did I video? Yeah, pause recording, stop recording.